You're listening to MedX, the Medical Extrusion Podcast. Presented by U.S. Extruders. Extrude with confidence. Custom extrusion equipment designed for you and your application.
Welcome to the MedX Podcast. This is Steve Maxson. This is part 2 of our conversation with Teddy Mudge of Hoop Medical. In this episode, we discuss some of the processes upstream of the balloon forming process that impact balloon performance. We also talk about the differences in balloon types that deliver devices versus balloon types that deliver energy. I hope you enjoy. In terms of extruded medical tubing that you are secondarily forming, balloon tubing has more stringent quality requirements, right? Beyond dimensional specifications.
Yeah.
And that is because, as you've alluded to, you are longitudinally and radially expanding the tubing to enhance the mechanical properties. And this is where the concept of garbage in, garbage out applies, right?
Yeah.
In order to have quality output.
Yeah, exactly.
Walk us through some of the processes upstream of the balloon forming machine.
Yeah.
Such as material handling to avoid particulates, gels, moisture levels, or during extrusion, the concentricity level, or if there's too much shear imparted in the extrusion during the process. Walk us through some of the factors that contribute to high quality, high performance, repeatable balloon forming process.
Yeah. Okay, cool. Yeah. So you're dead right there. It's very much a garbage in, garbage out process. And so basically we need to be working with the best quality balloon tubing extrusion that we can get our hands on. And you'd be amazed, but there's only a few people in the world who can actually make that tubing to those standards. And so we source tubing from a number of different suppliers. We don't do it ourselves in-house. So I don't want to come across as a balloon tubing expert, because I'm not. But what I can say is getting the tubing right is paramount to having a chance at making the balloon. So yeah, as I said, there's a few people around the world who really know these subtleties well, and they're the ones who we work with and who we'd be interested in working with. And you touched on, dimensional tolerances being important. Included in that is obviously your ID and OD of the tube, but also concentricity, how concentric that ID is with respect to the OD. Keep in mind, we're trying to form a balloon which may very well have a wall thickness as thin as 5 microns. And so if that's the end goal, to have a balloon that might have a very thin wall around 5 microns, you can imagine how important it is that the tubing that you start out with is concentric, because if you start with even the slightest eccentricity or non-concentric tubing, you're going to get a wall on your balloon on one side which might be 2 microns and on the other side which might be 10 microns, because you started off with tubing that wasn't concentric. So that's kind of super important. You also mentioned shear, and that also affects, like you can get 2 tubes from the same material to the same dimensional specifications. So the ID/OD tolerances are good. The concentricity is good. The material cert is good. They're both from the exact same grade of resin. Could even be from the same lot of resin. So if we remove any variability that there might be in the resin manufacture, and you then extrude it, and you do it, you get those tolerances and you get those dimensions to work with one set of extrusion settings, and then you get the same dimensional tolerances to work with another set of extrusion settings. The second set perhaps having a lot of shear on the extrusion, but those 2 balloon tubes, when you try and make balloons with them, will perform very differently in our process. And so one of the things, depending on the balloon and depending on the application, one of the things we'd be looking at is how does that balloon tubing elongate? Like, how does it, when you stretch it, what kind of forces are involved? What's the ultimate elongation? Things like that. And those are sometimes telltale signs to a process upstream from us that wasn't quite right. Obviously, we've got all the control measures in place to check that things were made within certain limits, but it's good to have a fail-safe check as well, which we do. So all of the balloon tubing extrusion which we source from around the world goes through a real stringent incoming inspection at Hoop, and we'll pick up before we even try to make balloons. We'll pick up that there's a problem. We don't want to waste 3 days on our machines figuring out that it's actually an extrusion problem. So we have those checks and balances in our incoming inspections. And I mean, even aside from the extrusion and how important it is that that's done right, even upstream from there, the compounding of the resin, and you mentioned earlier drying, but also, foreign particulate that might come in, or if you've got in your compounding, maybe you've got some old burnt material in there, or in maybe one of your extruders in one of the screws, there's some burnt material on the screw that's kind of flaking off into the, all those things would have a negative effect on us. So visual inspections are a big thing. Gels, fish eyes, controlling for those. But I suppose another kind of nuance is, and something most people don't really think about, like if you look hard enough at any extruded tube, you're going to find some visual defects. If you magnify in enough, you will see some areas looking different to others. And it's about understanding where those limits should be. What are we going to pass and what are we going to reject? Because if we zoomed right in and looked for anything and then reject it, we would unfortunately reject all material. So it's important to understand at what level it actually impacts the performance of the balloon, because that's what all these controls are about, and that's why we have regulations in place, and that's why they're important, is to track when there's a process or a material change that's going to actually negatively impact the performance or the safety of the product. In our case, that's a balloon. Right. So understanding what you can live with and what is acceptable and what is not is also a big part of it. And I think these days, more and more, vision systems are getting cheaper. People are able to see things that they weren't able to see a few years back. And so that point that I'm making there is becoming more and more important. Where do you draw the line? And and then how best do you control for those things?
Okay, excellent. Let's move on to a little bit more about applications and therapies. A large portion of balloons, non-compliant, semi-compliant, are used to deliver devices. You talked about delivering a stent earlier. It might be a heart valve. And over the years, we've seen a tremendous growth in balloon-based ablation catheters. We have electrophysiology to treat AFib, renal denervation to treat hypertension. And these often use what's called hot balloons, where electrodes are mounted to the body of the balloon and they deliver RF energy, or cryo balloons that deliver, cryothermal freezing energy to ablate soft tissue. Walk us through some of the differences in the balloon types, materials, maybe compliance levels, balloons that are used to deliver devices compared to balloons that are used to deliver energy.
Yeah, okay, sure. So I think one of the first things that kind of strikes me there is probably around balloon shape. If you look at balloons that deliver devices or implants, that it's typically a tubular shape implant or cylindrical shape implant, often comprising some stent-like element. So those are often tubular in shape, and so the shape of balloon needed to deploy that is a cylindrical standard shaped balloon, what we would call a standard shape. I mean, it's basically got a cone on each end and then a cylinder in the middle. And so, yeah, many of your balloons which are delivering devices would look like that kind of shape. But then another interesting thing to talk about is materials. And often what everyone's trying to do with a balloon is get enough force to do the work. So if the work is in putting a stent in, have enough radial force to actually deploy that stent to the right size. In balloon terms, that comes down to the pressure that's inside the balloon. So it basically boils down to having a burst pressure or a rated burst pressure that is high enough for the job. And then coming from the other side, most customers want the balloon to have the lowest profile possible when it's folded down and when it's going into the body, because most of the time, you ask any interventional cardiologist or any surgeon that does this type of work, how can we make this better? They will always want it to be smaller when it goes in. But when it gets into position, they always want it to be big enough to do the job. So what that boils down to in balloon speak is having a real thin wall thickness, yet still being able to reach those high pressures. And I mean, it's I mean, a part of why we're called hoop is when you inflate a pressure vessel with a certain wall thickness, and you inflate it with a certain pressure, you develop this hoop stress in that pressure vessel, and that's pretty much the stress running in the circumferential direction. So the stress running in a ring shape around the balloon. And that's called hoop stress in mechanical engineering. And so what you're looking for is a combination of wall thickness and material that is going to give you an optimized balloon, one that reaches the burst pressures needed, but is also as thin as it can be, so that you can get it as small as you can, to gain access to the body easily. And so that's like the typical challenge when it comes to balloons that are deploying devices or implants. Balloons that are used to deliver energy, you're right, there's been a lot of innovation there in the last 10 years. And you touched on a few of them. So often these balloons are trying to ablate tissue, which basically means, in layman's speak, like burn the tissue or scar the tissue or get the tissue to go from being normal tissue to scarred tissue. And that might seem counterintuitive, but an example would be in your heart, you have this thing called the bundle of His, which is like the electric system of the heart. And when you mess with that electric system, it affects your heartbeat. And humans cleverly found out that by burning tissue near some of those nerves in the heart, you can change the rhythm of the heart. So you can take a heart that's developed arrhythmia, where it's no longer beating in sync, and by burning very specific little parts of the inside of the heart, you can get that rhythm back, and you can restore the rhythm to someone's heart. And to do that burning work, I'm not a doctor, I'm just, it's not the right terminology, but to do that work, you need to deliver energy. And it might be through actual heat, or through radio frequency, or through light, for example, like laser. And often when you're delivering that energy, you need a way to approximate the tissue. So if you just had, like, for example, a little heater element, and you've got that heater element on a little catheter, and the idea is you're going to go up into the heart and you're going to burn some tissue, you're going to ablate some tissue, and you need a way of getting that little heater element to actually touch the tissue, and that's often where the balloon comes in. You mount that element onto the outside or inside of the balloon, and you get it into position. And when you're in position, you inflate the balloon, which pushes that little energy transmitter up against the target anatomy, and then you deliver your therapy. And so what does that mean? It means that the balloon often needs to be the right shape for the destination or for the target anatomy. And often the standard shape balloons, that's where the balloon industry comes from, are not the right shape. You might be trying to go into the atrium of the heart, and so you might need something that is like a squashed sphere, more of a spherical shape or a short spherical shape.
Right.
Or you might be going to some, I don't know, like a branch vessel, and you might need a balloon that looks like a Y. All sorts of shapes are possible and needed for these different applications. And so that's really where customers can leverage our experience when they come and work with us, is basically explaining the problem to us of what they want their balloon to do, and allowing us to have input on things like materials, tooling, what can be expected from pressures, wall thicknesses, these nuances around balloons, where it actually takes quite a long time to get a feel for these things. And you can save a bunch of time by just coming and hiring us, and we'll do that work for you. So that's kind of the thinking behind the idea of working with an external supplier on balloons. A lot of our customers actually have balloon manufacturing abilities in-house, and that's really no problem. They come to us for the difficult ones, and I can help them through those. But yeah, I think I answered your question there, Steve, on the differences between the different types. I suppose, like, talking a little bit more to materials, often those energy delivering balloons or devices which might ablate, you can imagine there's often a balloon right next to something that is very hot or very cold, or very high energy, light intensity, or whatever it might be. And so, you need the balloon material to be able to withstand those environments, even if it's for a short while. And sometimes some of these devices have kind of backup balloons. Like, if things don't go well, there's a backup balloon to catch whatever might otherwise have leaked out. And so, redundancies in place to ensure that these procedures are safe. And so, we have, we've worked on projects where there's a balloon inside another balloon, or two balloons butting up against each other, or multi-layered balloons made from different materials at different layers, and all sorts, really. And so it's fun to be in this position that I find myself in, actually, because I get to, obviously now with confidentiality in place, but I get to see a lot of the cool new things that are being made at the moment. And as you'll know, these devices can take 3 to 7 years to actually get to market. And they need to go through all sorts of benchtop V&V, and then clinical trials, and so on and so forth. And this all takes time. So I'm in this great, really what I consider a fortunate position, where I get to see some of these devices of tomorrow before other people, which is pretty cool. Yeah.
Right. Very exciting.
Yeah.
One last question. You talked about a balloon in a balloon or multiple balloons. Are there ever situations or designs where you have different compliance levels with the different balloons, more of a compound compliance?
Yeah. I think so you can get there's different things you can do. You can engineer in different compliance into a different portion of the same balloon. Compliance can be controlled in a number of different ways. It's not just that material that you select when you start. It's also the processing that you do to that material, both at the extrusion level, but also at the blow forming level, mostly at the blow forming level. And so, yeah, I mean, theoretically, and not even theoretically, actually proven, we can make a balloon which had less compliance on one end and more compliance on the other end, and same diameter, same thickness. Or we could have a balloon that is almost acting like a jacket in a certain portion of have like a balloon assembly with an inner and an outer balloon. And I'm talking more and more these days about this concept of a balloon module, where sure, we make balloon components, but often that balloon component might actually be made up of two subcomponents or more that have been bonded together in some way, or connected together in some way, or maybe made in the same process together. But where and I'm finding as the industry evolves and as the technology keeps moving forward, people are coming to us with even more imaginative ideas and imaginative ways of using balloons. And we encourage that. We want to be that partner who does that kind of work. So alongside the balloons that we make and the standard balloons that you would see on our website and on the internet, there are these other projects going on where it's more of like a sub-assembly, what I call balloon module. And what's needed often is like some form of secondary process there, maybe a bonding process, maybe some kind of cutting process or that sort of thing, where the balloon needs more work, and we're developing some of those processes at the moment as well. So we're wanting to position ourselves that we're very focused on the balloon, but that we are not shy to take on challenging balloon problems that might require more than just one balloon. So I don't know if I've made that clear. We're very much focusing on the balloon module or balloon sub-assembly, not the full device.
Right.
Yeah, I mean, an example of that would be like braid reinforced balloons, for example. Like there's a technology which allows dilation balloons or high pressure balloons to reach even higher pressures for a given wall thickness. And they do this by reinforcing that balloon material with some other material and forming a composite. And that type of work, yeah, we're super interested in it. Anything that pushes the boundaries of what balloons can do. Yeah.
Okay. Wow, very interesting. I could ask you hundreds of questions about balloon forming, but we'll save that for another day, right?
Yeah. I don't want to bore people with this stuff. It's pretty niche.
No, it's very exciting. But we thank you for joining MedX podcast and sharing your thoughts, and we'll be sure to get you on another time so we can talk about some of these other interesting topics related to balloon technologies.
Oh, well, that's awesome. Thanks, Steve. Yeah, it's been a real pleasure. Yeah, happy to join again sometime, and good luck with the show.
Thank you so much.
Cool. Cheers.
Thank you for listening to MedX, the Medical Extrusion Podcast, presented by US Extruders. Please subscribe to make sure you're getting the latest episodes. All links are available in the show notes.